Welcome to the first installment of Relax and Learn by Valearnis. Today's session will cover the vast and enigmatic aspects of our universe, from solar system formation, comet pathways, all the way down to how gravity influences everything around us. Sit back and relax while we drift through the cosmos together. Long before any planets formed, the universe was a sea of hydrogen and helium. These light elements drifted in vast, silent clouds called nebulae. They were so spread out that for millions of years, almost nothing happened. But over time, gravity, nature's quiet sculptor, began to pull these wisps together. Slowly, almost imperceptibly, the gas grew denser in certain regions, forming knots and clumps inside the darkness. Imagine, if you will, a cold, dark cradle where new stars begin to form. These places are known as stellar nurseries. Within these nurseries, dense pockets of gas and dust grow heavier as gravity draws in more and more material. If you could see it with your eyes, it would look like a gentle fog thickening into swirling shapes. As the gas compresses, it heats up. Deep inside, at the very center of the clump, temperatures rise so high that atoms begin to fuse together, releasing brilliant energy. A newborn star ignites, its light piercing the shadows that have persisted for countless ages. Sometimes, these births are triggered by more violent events. Far away, another massive star may have reached the end of its life, exploding in a powerful supernova. The shockwave from this explosion races across space, compressing the clouds it touches. This sudden jolt can tip a delicate balance and set in motion the collapse that will eventually create new stars and solar systems. In this way, endings become beginnings, and death in the cosmos leads inevitably to rebirth. As the protostar grows brighter, it is surrounded by a spinning disk of leftover gas and dust. This is called the protoplanetary disk. You can imagine it like a vast, flat ring encircling the newborn sun, a place where the seeds of planets are scattered and waiting. Within this disk, countless tiny grains of rock and ice drift and collide. Some stick together, building larger and larger clumps. Each of these fragments feels a faint tug of gravity from the young star at the center, guiding their paths in elegant spirals. Over thousands and millions of years, these grains become pebbles, then boulders, and finally massive bodies called planetesimals. They sweep through the disk, gathering more material as they go. It is a slow dance of attraction, collision, and merger. The process is so gradual that if you watch for a lifetime, you might see almost no change at all. And yet, given enough time, whole worlds take shape. Different parts of the disk give rise to different kinds of planets. Close to the young star, the heat is intense, and lighter gases are swept away by solar winds. Here, rocky planets like Earth and Mars will eventually form, dense and solid. Farther out, where it is colder, ices and gases can remain. In these distant regions, giant planets will grow, huge spheres of hydrogen and helium, surrounded by dozens of moons and rings of ice. While the planets assemble, the young star continues to mature. It begins to burn more steadily, its powerful radiation gradually pushing away the remaining gas and dust. This clearing marks the end of the main phase of planet formation. What is left behind are the building blocks of a solar system: planets, moons, comets, and asteroids, set in motion around their shining star. Though we often imagine our sun and planets as isolated, they were born alongside countless other stars. Stellar nurseries can form entire clusters, hundreds or even thousands of stars coming to life together, like candles kindling one by one in a vast dark hall. Over time, gravity and motion scatter these stars across the galaxy. Some drift away alone, while others remain bound in clusters, orbiting one another for billions of years. When you look up at the night sky, you are seeing the distant light of other stars that once began in similar clouds. Every point of light carries the story of a birth like this. silent clouds collapsing, igniting, and shaping new systems that may one day harbor life. Even now, somewhere in our galaxy, new stars are being born. The same processes that created our sun and the earth beneath your feet are happening again and again, writing new chapters in the universe's endless story. At the most basic level, everything in a solar system begins with hydrogen and helium, the two simplest elements in the universe. These gases were born in the Big Bang, nearly 14 billion years ago, when the universe itself was young and hot. Over time, these primordial elements cooled and spread out, filling the vastness with a thin mist that would someday become stars and planets. But hydrogen and helium alone are not enough to create the rich variety of worlds we see. Heavier elements, like carbon, oxygen, silicon, and iron, are needed to build solid planets, moons, and the complex molecules that make life possible. These elements are created deep inside stars in the intense heat and pressure of their cores. As stars live and die, they scatter these materials back into space. Every rock and drop of water, every mountain and ocean comes from this cycle of birth and death. You and everything around you are made of atoms forged in the hearts of stars. When a new solar system begins to form, all of these ingredients gather in a spinning protoplanetary disk around the newborn star. This disk is a flat, swirling expanse, stretching for billions of kilometers in every direction. In the inner regions, close to the heat of the star, rocky materials dominate, tiny grains of metal and silicate minerals. Farther out, where temperatures are much colder, water ice, methane, and ammonia freeze solid, joining the mix. This disk is a kind of cosmic kitchen. The star is the glowing stove at the center, warming everything nearby. The ingredients, dust, ice, gas, are scattered everywhere, blending and separating depending on distance and temperature. In this kitchen, the recipes are guided by the laws of physics. Over millions of years, the smallest grains begin to stick together, forming larger and larger clumps. Electrostatic forces help at first, like static cling making particles adhere. Then, as these clumps grow, their own gravity begins to pull in more material. The process is slow, but it is relentless. A pebble becomes a boulder becomes a mountain drifting through space. These growing bodies sweep up everything in their paths, cleaning out lanes in the disk as they travel in circles around the star. These are the first planetesimals, baby planets in the making. Different parts of the disk produce different kinds of planets. In the warm inner regions, gases are too energetic to stay bound to small bodies, so the solids that survive are metals and rocks, dense materials that will eventually form terrestrial planets like Earth and Mars. These worlds are built from heavy elements that cling together despite the heat, forming solid crusts and iron-rich cores. In the cooler outer regions of the disk, something very different happens. Here, ices remain solid and gas can linger in thick envelopes. As icy planetesimals grow, they reach a size where their gravity becomes strong enough to hold onto vast amounts of hydrogen and helium. This is how the giant planets are born, massive spheres with deep, swirling atmospheres. Jupiter, Saturn, Uranus, and Neptune all formed in this frigid zone, becoming worlds far larger and heavier than any rocky planet. But not all material becomes part of a planet. Some remains in belts and clouds, endless swarms of comets, asteroids, and icy fragments that never coalesced into something larger. In our solar system, the asteroid belt between Mars and Jupiter is one such place, a region where the gravity of the giant planets kept the ingredients from gathering into a planet. Far beyond Neptune lies the Kuiper belt, filled with frozen relics like Pluto, and even farther still, a vast invisible halo called the Oort cloud. These regions hold some of the most ancient, unchanged material, preserving the early history of the solar system like a time capsule. All these components, rock, ice, gas, and dust, combine in countless ways to create the diversity of worlds we observe. Some solar systems have massive planets hugging close to their stars. Others are filled with rocky planets or littered with debris. The mixture of ingredients, the distance from the star, the turbulence in the disk, and the gravitational influences of neighboring stars all play their part in shaping the final outcome. If you imagine yourself floating within a protoplanetary disk, you would see a softly glowing fog stretching from horizon to horizon. Tiny specks would drift past your eyes, grains smaller than a grain of sand, each one destined to become part of a world or remain forever adrift. Occasionally, a flash of light would mark the collision of two larger bodies, sending out a spray of molten fragments. Over millions of years, this quiet, persistent process sculpts the architecture of a solar system. Even today, astronomers observe these disks around other stars, using powerful telescopes to peer into the birthplaces of alien worlds. In some images, you can see dark lanes where planets are already forming, sweeping clear their orbits. These distant disks are reminders that our own solar system once looked much the same, a swirling blend of gas and dust, patiently assembling the planets and moons we know. As you breathe slowly and let your thoughts drift, consider the humble beginnings of everything we see. From simple hydrogen atoms to complex molecules and icy fragments, all the ingredients of creation lie waiting in the darkness, drawn together by gravity's quiet hand. And in this cosmic recipe, the smallest specks of matter can, given enough time, become something magnificent. A planet, a moon, or perhaps even a world that harbors life. Chapter 3. The Architecture of Our Solar System. As you rest in the quiet of your room, think of the sun rising in slow motion, flooding space with golden light. Its warmth reaches across billions of kilometers, touching everything that circles it. This is our solar system, a vast family of planets, moons, and countless smaller companions, all bound together by the sun's gravity. At the heart of this system lies the sun itself, a star that holds more than 99% of all the mass in the solar system. Its gravity is the glue that keeps everything in orbit. If the sun were the size of a large exercise ball, Earth would be a tiny bead circling many meters away. And even the farthest planets, so distant that their sunlight arrives hours after it leaves the sun's surface, remain locked in their graceful, endless paths. Closest to the sun are the inner rocky planets, small and dense worlds shaped by intense heat. Mercury is the first, a scorched, cratered sphere that spins slowly, baking under unfiltered sunlight. Its thin exosphere barely counts as an atmosphere, and its days and nights bring temperature swings more extreme than almost anywhere else in the system. Next comes Venus, cloaked in thick clouds of carbon dioxide and sulfuric acid. Its pale yellow atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet of all. Beneath the clouds, the surface glows with volcanic plains and highlands, hidden from view but revealed by radar maps. Despite its beauty, Venus is a place of crushing pressure and searing heat, a warning of what can happen when a planet's atmosphere tips out of balance. Our own Earth follows, a unique blue oasis, covered in oceans and teeming with life. From space, it is a bright marble, wrapped in white clouds. Its perfect balance of warmth and liquid water makes it a rare gem among the countless planets. Earth's companion, the Moon, orbits nearby, gently tugging at tides and stabilizing the planet's tilt. Together, they move around the sun in a dance that has lasted for more than 4 billion years. Mars is the last of the rocky planets, a rust-colored world with canyons, volcanoes, and polar ice caps. Though now cold and dry, it once had flowing rivers and perhaps shallow seas. Today, its thin atmosphere lets the sun's radiation reach the surface unhindered. Robotic explorers roam its deserts, searching for clues to a warmer, wetter past. Beyond Mars lies a region unlike any before it, the asteroid belt. Here, countless rocky fragments orbit between Mars and Jupiter, Some are as small as pebbles, while others, like the dwarf planet Ceres, are hundreds of kilometers wide. These leftovers of planet formation are reminders of a time when the solar system was young and chaotic. Past the asteroid belt, the solar system opens up into a realm of giants. Jupiter comes first, the largest of them all. This immense planet is more massive than all the other planets combined. Its swirling atmosphere is striped with colorful bands and storms, including the Great Red Spot, a vast hurricane that has raged for centuries. Jupiter's powerful gravity shapes the orbits of countless asteroids and comets, acting as both protector and disruptor. Orbiting Jupiter are dozens of moons, each unique. Among them, icy Europa hides a deep ocean beneath its frozen crust. Ganymede is the largest moon in the solar system, bigger even than Mercury. Io, closest to Jupiter, is alive with volcanic eruptions that constantly resurface its landscape. Saturn follows, famous for its brilliant rings, delicate bands of ice and dust encircling the planet in perfect symmetry. Saturn itself is a gas giant like Jupiter, with powerful winds and a hazy atmosphere rich in hydrogen and helium. Its moons include Titan, a world with thick clouds and methane lakes, and Enceladus, which sprays geysers of water into space. Farther still, the ice giants Uranus and Neptune drift in the cold twilight. Uranus rotates on its side, a world tipped over by an ancient collision. Its pale blue-green color comes from methane in the atmosphere, which absorbs red light and scatters blue. Neptune, the farthest of the giant planets, is a deep azure sphere with fierce winds and dark storms that sweep across its surface. Beyond Neptune lies the Kuiper Belt, a vast collection of icy objects. Among them is Pluto, once considered the ninth planet, now reclassified as a dwarf planet. Pluto is a place of nitrogen ice, towering mountains, and a thin, ghostly atmosphere. Its companion Charon is nearly half its size, forming a double world locked together in mutual orbit. Even farther out, invisible to most telescopes, the solar system extends into the Oort cloud, a spherical shell of icy fragments stretching almost halfway to the next star. Here, trillions of comets drift in darkness, waiting for some distant disturbance to send them inward on a long, looping journey toward the sun. Throughout this entire system, everything is in motion. Planets follow their orbits year after year, moons circle their hosts, comets trace vast ellipses, and the sun itself moves around the center of the Milky Way. From the smallest asteroid to the largest gas giant, each object follows the subtle curves set by gravity's steady hand. Chapter 4, Planet Formation, From Dust to Worlds. All around you, an endless haze of fine dust and gas glows in the faint light of a newborn star. Though it looks peaceful, this place is alive with motion and quiet transformation. Here, in this delicate fog, worlds are about to be born. It begins with grains of dust, microscopic flecks of rock, ice, and metal drifting through the protoplanetary disk. Each tiny particle is so small you could hold thousands on the tip of your finger, but together they make up the raw material from which planets emerge. The process that turns them into something larger is called accretion, a word that means growth by gradual gathering. In the earliest stages, forces as simple as static electricity help these grains stick together. Like particles of flour clinging when you rub them between your palms, dust grains collide gently and join, forming clumps no bigger than a snowflake. In the cold, dark reaches of the disk, this dance goes on for thousands of years. Bit by bit, the clumps grow heavier. Every time they meet, they have a chance to stick and become something larger. Over time, these clumps evolve into pebbles and then into boulders meters or kilometers across. As their size increases, gravity begins to play a stronger role. No longer limited to random collisions, the growing bodies can now attract other fragments from a distance. They become planetesimals, the building blocks of planets. Imagine drifting near one of these early planetesimals. It would look like a dark, irregular rock tumbling silently through space, Its surface might be pitted from impacts and coated in frost where ices have condensed. If you watched for 1,000,000 years, you'd see its size increase as it swept up smaller debris, a patient collector in an endless storm of drifting material. In some regions of the disk, planetesimals collide so often that they merge into larger bodies called protoplanets. These are massive enough to dominate their orbits, clearing out a path through the fog of dust and smaller rocks. When two protoplanets meet, the collision is cataclysmic. Entire mountains vaporized in an instant, molten oceans splashing into space. Such impacts are rare, but they are decisive, reshaping worlds in moments of unimaginable violence. Our own planet was forged in such collisions. Scientists believe that in Earth's earliest days, it endured a colossal impact with a Mars-sized body. This event ejected a ring of molten debris that later coalesced into the Moon. Even today, the scars of these ancient impacts can be seen on many worlds, etched into their surfaces as vast craters and basins. Meanwhile, farther from the Sun, a different kind of growth unfolded. In the cold outer regions of the disk, planetesimals of rock and ice grew large enough to capture gas from the surrounding nebula. These bodies became the cores of gas giants, Jupiter and Saturn. As they gathered thick blankets of hydrogen and helium, they swelled to immense sizes. Around them, their own miniature disks formed, spawning dozens of moons and delicate rings. This contrast between the inner and outer solar system, rocky worlds close to the Sun, giant planets farther away, emerged naturally from the physics of temperature and distance. In the warm interior, volatile gases escaped, leaving behind dense, rocky materials. Beyond a certain line, called the frost line, ices could survive, adding mass to growing planets and enabling them to capture gas. While the main planets were forming, countless smaller objects remained scattered throughout the disk. Some stayed as asteroids or comets, never gathering enough material to grow larger. Others were ejected by gravitational encounters, flung out into interstellar space to drift forever between the stars. Gradually, as the young sun grew stronger, its radiation began to clear away the leftover gas and dust. The solar wind, streams of charged particles streaming outward, swept the protoplanetary disk clean. Only the finished worlds and their debris remained, circling the sun in newly established orbits. Picture this moment in time, a solar system still warm from its birth, planets cooling from their last impacts, moons settling into place. The surfaces of these new worlds were often oceans of molten rock, their skies filled with toxic gases and showers of meteors. Yet hidden in all this chaos was the foundation of everything to come: oceans, continents, and eventually life. Over hundreds of millions of years, the collisions grew less frequent, the planets calmed, their surfaces hardened, and their atmospheres evolved. Some, like Earth, retained just enough gas to form an atmosphere and oceans. Others, like Mars, lost much of theirs to the solar wind. The gas giants held onto their thick envelopes of hydrogen and helium, becoming miniature solar systems of their own. Even today, the evidence of planet formation surrounds us. The moon preserves the memory of ancient impacts. Meteorites that fall to Earth are pieces of planetesimals from the dawn of the solar system. Comets that visit from the edge of the Oort cloud carry ices unchanged since the sun was young. Chapter 5: Moons, Rings, and Other Companions. While the planets themselves are often the focus of our attention, they are rarely alone. Scattered around them are moons that tug and pull, rings that shimmer in delicate arcs, and smaller bodies that trace their own quiet paths. Together, they create the rich tapestry of a solar system, more varied and beautiful than any single world alone. From the beginning, as planets were forming out of swirling disks of dust and gas, many moons were born alongside them. Some of these moons are ancient companions, created from the same material as their parent planet. Others arrived later, captured by gravity after wandering too close. A few formed when colossal impacts shattered young worlds, sending debris into orbit that later gathered into a new body. Each moon holds a story about how its world came to be. If you were standing on the surface of one of these moons, you might feel only a fraction of Earth's gravity, and when you look up, your sky would be dominated by the nearby planet, looming huge and bright, a constant reminder of the gravitational bond that holds you there. The Earth's moon is our most familiar companion, a silent witness to the evolution of our planet. Its surface is scarred by billions of years of impacts, vast basins and bright rays of debris spreading across the grey dust. Long ago, when the moon was still hot and molten, enormous lava flows filled the lowlands, creating the dark plains we see today. Every night when we look up, we are seeing a landscape frozen in time, largely unchanged since the earliest days of the solar system. Beyond Earth, the diversity of moons grows astonishing. Mars, though much smaller than Earth, has two tiny moons, Phobos and Deimos, captured asteroids that now orbit as dark, potato-shaped companions. They circle Mars swiftly, especially Phobos, which rises and sets in the Martian sky more than once each day. When we move farther out to the giant planets, the true abundance of moons becomes clear. Jupiter alone has at least 95 known moons and possibly more. Some are small, irregular fragments. Others are vast and complex worlds in their own right. Ganymede, Jupiter's largest moon, is bigger than Mercury. Beneath its icy surface, scientists believe there may be an ocean of liquid water, a hidden sea that could contain the basic ingredients for life. Europa, another of Jupiter's moons, is smaller but no less intriguing. Its bright, smooth crust is streaked with dark lines where the ice has cracked and shifted. Beneath the frozen shell lies yet another subsurface ocean, warmed by the tidal forces that flex Europa's interior. Occasionally, plumes of water vapor burst through the ice, spraying into space. These geysers offer glimpses of the ocean below, an environment perhaps not so different from Earth's deep-sea vents. Io, by contrast, is a world of fire. It is the most volcanically active body in the solar system. Hundreds of volcanoes dot its surface, some erupting lava fountains dozens of kilometers high. Io's strange landscape is colored by sulfur and frost, a reminder that even moons can be places of dramatic energy and change. Beyond Jupiter, Saturn has its own collection of wonders. Its largest moon, Titan, is unique, wrapped in a thick golden atmosphere of nitrogen and methane. Beneath the hazy sky, rivers and lakes of liquid methane and ethane flow across the frozen ground. On Titan, rain falls from orange clouds, sculpting channels and deltas in a landscape eerily similar to Earth's, though unimaginably cold. Saturn's small moon, Enceladus, is one of the most beautiful and surprising places in the solar system. Its bright surface gleams with fresh ice, and from fractures near its south pole, geysers of water erupt into space, feeding Saturn's rings and hinting at a warm ocean beneath the crust. In 2015, a spacecraft flew through these plumes, detecting organic molecules, ingredients for life drifting in the dark. And then there are the rings themselves, Saturn's most famous adornment. From a distance, they look like solid bands encircling the planet, perfectly smooth and continuous. Up close, they are revealed to be countless particles, chunks of ice and rock ranging from dust grains to boulders, each following its own orbit. The rings are dynamic and ever-changing, sculpted by the gravity of Saturn's moons into delicate waves and gaps. They are thought to be either ancient remnants of the solar system's formation or the remains of a shattered moon. Other giants have rings too. Jupiter, Uranus, and Neptune each possess faint, narrow rings composed mostly of dark dust. These structures are subtle, sometimes only visible when backlit by the sun. They are reminders that the forces that shape moons can also create rings, through collisions, tidal disruptions, or slow accumulation of debris over eons. Beyond the major moons and rings, there are countless smaller companions, asteroids captured in orbit, shepherd moons that keep rings in line, and Trojan objects that share a planet's path around the sun. Even Pluto, once considered a lone outpost, has 5 known moons. The largest, Charon, is so big relative to Pluto that the two bodies actually orbit a point in space between them, locked together in a gravitational embrace. If you are drifting high above Saturn's rings, below you stretches a landscape of countless icy fragments, circling in perfect silence. Every so often, a tiny moon passes through, carving channels and waves in the ring particles. Farther out, larger moons orbit in measured rhythm, their gravitational pulls gently guiding the smaller debris. From this vantage point, the complexity and elegance of a solar system becomes clear. Planets are not alone. They are part of families of worlds, each interacting in ways large and small. In every solar system, moons and rings tell stories of formation, destruction, and renewal. They are reminders that even in the darkness, beauty can emerge in the most unexpected forms. Glittering arcs of ice, volcanic plumes, or hidden oceans waiting beneath shells of frozen rock. As you drift in thought, consider how these companions have shaped their planets. The moon steadies Earth's tilt, creating the cycles of seasons. Jupiter's moons influence the giant planet's magnetic field. Saturn's rings reflect sunlight, transforming the night sky into a spectacle of shimmering bands. All of them are part of the quiet, ongoing story of the solar system. Chapter 6: How Solar Systems Move Through Space. So far, we've explored planets and moons, dust and ice, rings and oceans hidden beneath frozen shells. But tonight, we take a deeper journey, not just around the sun, but through the vast ocean of the galaxy itself. Because a solar system, for all its gravity and order, does not stand still. It is not an island but a ship, sailing through the galaxy at breathtaking speed. From afar, our solar system appears as a tiny, glowing mote, circling one spiral arm of the Milky Way. And like all stars and their families, we are in constant motion, forever pulled by unseen forces across incomprehensible distances. Let's begin at home. Our Earth orbits the Sun at about 30 kilometers per second, fast enough to circle our star once every 365 days. This is the motion we know best, the rhythm of our seasons, the passage of years. But the Sun itself is also moving, carrying Earth and every planet with it. Our entire solar system is hurtling through space at about 828,000 kilometers per hour, tracing a broad path around the center of the Milky Way. The Sun is a glowing firefly, and trailing behind it is a swarm of tiny sparks. Planets, moons, comets, all following in a long spiral as the Sun flies onward. Some astronomers describe the solar system's path as helical, like a corkscrew spinning through space. The planets orbit, yes, but they do so while being pulled forward by the Sun's greater journey. We orbit the galactic center once every 225 to 250 million years, a journey called a galactic year. That means Earth has only made about 20 full trips around the Milky Way since it formed. The last time we were in this part of the galaxy, dinosaurs were just beginning to appear. Before that, forests of giant ferns covered the continents. Each galactic year holds the rise and fall of entire species, the drifting of continents, and the slow evolution of life. As we make this vast arc, the Sun follows the Orion Arm, one of the spiral branches of the Milky Way. This arm is filled with gas clouds, young stars, and stellar nurseries. Sometimes we pass near other stars. Most drift quietly by at great distance, but on rare occasions one may pass close enough to disturb the outer reaches of our system, the icy Oort cloud, sending comets on long looping journeys toward the Sun. These stellar flybys, though rare, may shape the history of planets and even the fate of life itself. But the galaxy isn't empty, it's alive with structure. The Milky Way itself is a flattened spiral with a bright central bulge and winding arms that stretch outward like paint swirling on water. At the center lies a supermassive black hole, a region of unimaginable gravity that holds the galaxy together. All stars, billions upon billions, are in motion around this point, their orbits determined by the mass of the stars and dust within the galactic disk. The Sun's path isn't perfectly smooth. It bobs gently up and down as it orbits, like a boat on a slow tide. Every 30 million years or so, it passes through the galactic plane, an invisible sheet where the density of stars and gas is highest. Some scientists wonder if these crossings correlate with mass extinctions or comet showers on Earth. Though the evidence is uncertain, it's a humbling reminder that our solar system is part of a much larger, interconnected machine. Beyond the Milky Way, there are other galaxies, each one a swirling city of stars. The Andromeda Galaxy, our nearest large neighbor, is also moving. In fact, it's moving toward us. In about 4.5 billion years, the Milky Way and Andromeda will collide. But this will not be a crash in the way we think of cars or planets. Galaxies are mostly empty space. Stars will likely pass by each other without ever touching, but the gravitational ballet will reshape both galaxies into something new. In this ever-moving universe, nothing is truly still. Moons orbit planets, planets orbit stars, stars orbit the galaxy, and galaxies drift through clusters pulled by even greater structures, superclusters, filaments, and voids that make up the cosmic web. This web is the skeleton of the universe, an arrangement of matter so vast it defies imagination. But in all this motion you feel no wind, you hear no sound. Space does not resist our travel. The sun carries us effortlessly through the dark, its gravity a gentle hand guiding us along our spiral path. Comets fall inward, planets remain in line, and the invisible trail of our journey stretches for light years behind us. You are drifting beside the solar system just above the sun. You look down and see the planets tracing perfect circles, but from your vantage point, everything is moving forward. The whole system is a glowing swirl cutting through the black, leaving behind a trail of curved orbits like a ribbon streaming behind a dancer. In front of you, stars slide past slowly. Behind you, their light fades into distance. This journey isn't dangerous, it's part of the rhythm of existence. Even though we're moving at tremendous speed, we feel nothing. Day becomes night, the seasons pass, and the sky changes slowly over thousands of years. Constellations shift, stars grow brighter or fade. In ancient times, different stars marked the pole. In the distant future, others will take their place. And as we move, we carry with us all the materials and memories of our past. Asteroids that bear the chemical signatures of early Earth, comets formed in the coldest corners of the solar system, and light from the sun that once struck the oceans of Earth 1 million years ago, reflected, and began a slow journey into the void. Chapter 7. Exotic and Strange Solar Systems. Not all solar systems look like ours. In fact, the more we discover, the more we realize that our home system, with small rocky planets near the star and larger gas giants farther out, may be the exception, not the rule. Across the galaxy, there are planetary systems that defy expectations. Some stars are orbited by enormous gas giants that sit shockingly close to their host. So close, in fact, that their years last only a few Earth days. These are often called hot giants, massive planets that formed farther out but then drifted inward over time. In their tight orbits, they endure extreme heat and radiation. Some are so close to their stars that their outer layers are slowly evaporating, streaming away into space. In other systems, the opposite is true. Giant planets have formed and remained on the outer edges, far from the warmth of their star. They circle slowly, taking centuries to complete a single orbit. These distant giants sit in darkness, surrounded by cold, quiet moons, far removed from the chaotic inner regions. Even stranger are the worlds that orbit nothing at all. Sometimes, during the chaotic early years of a solar system's life, planets are flung away by gravitational encounters. These are called rogue planets, and they drift through the galaxy alone, without a star to orbit. Despite being cast out, many of them may still have atmospheres or internal heat. Some could even have deep, subsurface oceans, protected beneath thick layers of ice, strange, wandering worlds adrift in the dark. Other planets have even more unusual beginnings. A few orbit the remains of dead stars. ultra-dense objects left behind after a supernova. These stars are no longer warm or welcoming, yet they've gathered new material around them, and from this debris, new planets have formed. These are systems born from destruction. Their skies are dark, their stars faint pulses of energy rather than steady light. Some solar systems are home to multiple stars. In these, 2 or even 3 stars orbit each other, and planets must find their place in the ever-shifting dance. Some orbit tightly around just one star, while others orbit the entire group, circling all the stars at once in a wide path. Imagine standing on the surface of a planet in such a system and watching 2 suns rise, one after the other or both together, casting overlapping shadows. There are also systems filled with small rocky worlds packed close together, so close that one planet could loom large in the sky of another. These compact planetary families move in tightly choreographed orbits, their motions linked by delicate gravitational balances. Their arrangement is unlike anything in our solar system. And then there are the truly extreme planets, those that are scorched on one side and frozen on the other. Many of these are tidally locked, which means the same side always faces their star, just like our moon always shows the same face to Earth. On one side of these worlds, it's eternal day, bright and blistering. On the other, it's endless night, cold, still, and quiet. In between is a narrow band of twilight that could, in theory, be temperate enough to allow liquid water. Some planets have wildly stretched orbits, swinging in close to their star and then retreating far into the darkness. Their climates would be extreme, searing summers followed by deep frozen winters, each lasting years or even decades. And then there are the atmospheres. Some planets have skies filled with thick clouds of carbon and ash. Others may have glass particles in their upper layers, blowing sideways in high winds. The temperatures on some of these worlds soar to levels that would melt metal, while others may be colder than the most remote places in our own solar system. Even the types of planets vary. Many are unlike anything we have here. There are super-Earths, larger, heavier versions of our own planet, some rocky, some covered in vast global oceans. Others are miniature gas planets, small cousins of Neptune, shrouded in thick clouds and gas. These types of planets are among the most common in the galaxy, yet our solar system doesn't have either one. Stars themselves also shape the systems around them. Some stars are smaller and cooler than the Sun, glowing softly in red light. Their planets must orbit very close to stay warm, often circling in just a few days. Yet these small stars burn slowly and steadily, potentially lasting trillions of years, giving their planets a very long window of time in which life might arise. Other stars are massive and short-lived, burning hot and bright, then dying young in violent explosions. Around them, planets may form quickly, only to be lost again in the final blaze of their sun's collapse. And still, despite all this variety, patterns emerge. Planets are common, so common in fact that it's now believed nearly every star in the galaxy has at least one. There are more planets than stars. And while many are wildly different from the worlds we know, they're all shaped by the same processes: gravity, motion, heat, and time. Each system is a variation on a theme. Some are familiar, some are strange, some are like ours, just rearranged. Others are entirely foreign, but they all orbit, rotate, evolve. They are all part of the same grand experiment. Even now, telescopes around the world and above our planet continue scanning the sky, looking for the dimming of distant stars as planets pass in front of them, listening for the faint wobbles in a star's motion, or capturing the ghostly glint of a world faintly lit by its sun. Each new discovery adds a brushstroke to the picture. These distant systems remind us that the cosmos is far from static. It is dynamic, full of variety, and constantly surprising. Every time we think we understand what a solar system should be, we find another that rewrites the rulebook. Chapter 8. The Sun. Heart of our solar system, our last chapter for today. At the center of it all is a star. Everything in the solar system, from the planets to the comets, from moons to the tiniest specks of dust, moves under the influence of one object: the Sun. It is more than just the source of light and warmth. It is the dominant force, the oldest member of our system, and the reason anything exists here at all. The Sun holds over 99.8% of the total mass of the solar system. Every planet, every asteroid, every icy fragment is caught in its gravitational pull. Without the Sun, there would be no orbits, no stable paths, no heat, no life. From Earth, the Sun appears as a smooth, brilliant circle in the sky, but it is far from tranquil. Beneath its glowing surface, powerful processes are at work. The Sun is a giant sphere of plasma, made mostly of hydrogen and helium. At its core, temperatures reach over 15 million degrees Celsius. Here, hydrogen atoms collide with such force that they fuse into helium, releasing energy in the process. This fusion is what powers the Sun. That energy takes a long time to escape. Photons created at the core can take tens of thousands of years to make their way to the surface, bouncing and scattering through the dense layers inside. But once they reach the surface, they radiate outward into space, and eventually to Earth, where they warm oceans, power weather systems, and fuel photosynthesis in plants. The surface we see is called the photosphere, a region about 500 kilometers thick. Though unimaginably hot, it's the coolest visible layer at around 5,500 degrees Celsius. It's from here that most of the Sun's visible light escapes. But just above it lies the chromosphere and then the corona, the Sun's outer atmosphere, which extends millions of kilometers into space. Curiously, the corona is much hotter than the surface below it. The exact reason for this is still not fully understood, and it's one of the Sun's enduring mysteries. From time to time, darker regions appear on the photosphere. These are sunspots, temporary cool areas caused by intense magnetic activity. Sunspots often appear in pairs or clusters and can be many times the size of Earth. Though cooler than the surrounding surface, they're still thousands of degrees hot, and often associated with bursts of energy. These bursts are known as solar flares and coronal mass ejections. Solar flares release powerful streams of radiation, while coronal ejections hurl vast clouds of charged particles into space. If directed toward Earth, they can interfere with satellites, communication systems, and power grids. They also light up our skies with auroras, ribbons of green and red that shimmer near the poles, as solar particles interact with Earth's magnetic field. The Sun also emits a constant stream of particles known as the solar wind. This wind flows outward in all directions, carrying the Sun's influence deep into space. It creates a vast bubble called the heliosphere, a protective region that surrounds the entire solar system. The heliosphere helps shield us from high-energy cosmic radiation that comes from beyond the galaxy. Even at the edge of the solar system, far beyond Pluto, the solar wind is still present, though weak. Eventually it collides with interstellar space at a boundary called the heliopause. This is the true outer edge of the Sun's influence. Spacecraft like Voyager 1 and Voyager 2 have passed through it, sending back data from a realm no other probes have reached. For all its stability, the Sun is not unchanging. It follows an 11-year cycle, where magnetic activity rises and falls. During solar maximum, sunspots, flares, and ejections become more common. During solar minimum, the Sun appears calmer, though still active beneath the surface. The Sun's lifespan is immense, but not infinite. It is currently about 4.6 billion years old, and it has enough hydrogen to continue fusion in its core for another 5 billion years or so. But eventually that hydrogen will run low. When that time comes, the Sun will begin to change. First, it will expand. As hydrogen fusion slows, gravity will compress the core, raising temperatures and igniting fusion in the outer layers. The Sun will swell into a red giant, growing so large that it may engulf Mercury, Venus, and possibly Earth. The surface will cool and redden, solar winds will intensify, and the outer layers will begin to drift away into space. After millions of years in this swollen phase, the Sun will shed its outer shell entirely, leaving behind a glowing cloud of gas called a planetary nebula. At its center, all that remains will be a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen. It will no longer produce energy, only slowly cool over billions of years. That distant future is quiet and still, but today the sun is vibrant, powerful, and remarkably stable. Its warmth sustains Earth, its gravity keeps the planets in line, its cycles influence our magnetic field, our atmosphere, and even long-term climate trends. And it is not alone in its kind. Across the galaxy, stars like the Sun are common, classified as G-type main sequence stars. They represent a balance between size and longevity, power and predictability. Smaller stars live longer but burn more dimly. Larger stars shine brightly but burn through their fuel quickly and die in supernova. The Sun exists in the middle, a slow, steady, long-burning flame. Though average in many ways, the Sun is exceptional in what it has created. Around it, a system of planets took shape. One of them developed oceans. One of them grew forests. One of them began asking questions about the sky. There are other stars, larger and smaller. Some flicker, some pulse, some have already died. But for us, the Sun is the one that matters most. Its light touches every world in our system. Its gravity reaches even the farthest comets. Its history is written into the rocks of the Moon and the chemical fingerprints of meteorites. It is the oldest presence in our skies and the force that will still be burning long after every human structure has vanished. To observe the Sun is to look at the center of a story that's been unfolding for billions of years, and will continue for billions more. A story not just of light and gravity, but of formation, transformation, and inevitable change. We hope you enjoyed our first installation of Relax and Learn. Stay tuned for more.